Linear and exponential functions share many characteristics. This is because they're based on two different but similar sets of principles. So linear functions are based on repeatedly adding the same amount, which is using slope. Exponential functions is based on repeatedly multiplying by the same amount, so the base. So that's how you're going to get a difference between the two. So the two tables below represent a linear function and an exponential function, which is which, and explain how we arrive at our answer. So the first thing we're going to notice is that each one of them, x goes up by 1. So it's y that we're going to look at. If y is going up by the same rate every single time, then it's linear. So which one goes up by the same rate every single time? Well, it looks like table 2 is plus 3, plus 3, plus 3, plus 3. So it's repeated addition. So this one is linear. On table 1, it's times 2, times 2, times 2, times 2. So it's repeated multiplying, so it is exponential. So find the equation in standard form for each of the functions from the last one we did. Well, table 1 is easier. It's going to be the function of x. X is going up by 3 each time. And when x was 0, y was 8. Table 1, since that's exponential, it's a little bit different. Our f of x, we have to first think of, okay, what was our what's going to be our y-intercept? So when x is 0, what is y? Y is 5. And then it's being multiplied by 2 every time, raised to an exponent. Well, it's interesting that linear and exponential functions are ones where 2 points on the curve will always determine the equation of the curve. So consider the points 0, 12, and 1, 3. Create a linear equation that passes through these points, and y equals mx plus b. And an exponential equation in y equals ab to the x power form that also passes through them. Then, using your calculator, graph both using the window. So, we need to have linear and exponential. One thing we know is we know the y-intercept. So we know that so far our y-intercept is 12. So it's the other part that we don't know. So if this is linear and it's going up by the same amount each time, when x increased by 1, so when x increased by 1 from 0 to 1, y decreased by 9. So negative 9x plus 12. And then we look at, from an exponential side, as x increased by 1, so we multiplied by 1, the 12 goes to 3, which means that it divides by 4. So it's 1/4 to the x power. So we're now going to go to decimals, and then I will put the decimals screen up here, so you might want to pause now if you don't have this written down. So looking at the graph in decimals, the red graph is our linear, and the blue graph is our exponential. So you will see that our red graph, the y-intercept is still 12, and then it goes down at a constant rate. And then our blue graph still has a y-intercept of 12, but it goes down at an exponential rate. Recall that linear functions have a constant average rate of change, or a slope. That's, of course, why they have a constant amount added for every constant change in x. So let's examine the average rate of change for an increasing exponential. So this exponential function, f of x equals 4 times 2 to the x power, is shown partially in this table below. So find the average rate of change over the various intervals given. So this should be relatively simple because change of x is 1 every time. So going from 0 to 1, y increased by 4, so it's 4, or 4 over 1. Going from 1 to 2, remember our change in x is always 1. 8 to 16 is going up by 8. From 2 to 3, again, it's over 1, and it goes up by 16. And from 3 to 4, again, it's over 1, and it goes up by 32. Each one of these, because it's over 1, is just what the numerator is. So what is clearly happening to the average rate of change as x gets larger? It doubles. It doubles the y. So the fact that the slope of an increasing exponential is always increasing has an interesting consequence. So consider the linear function, y equals 20x plus 5, and the exponential function, y equals 5 times 2 to the x power. Both of these functions have a y-intercept of 5, so they start in the same location. So using our calculator, sketch these two curves on the axis below for the indicated window. Label each with its equation. So you'll see on the Desmos graph that I have on the right, the x-axis goes from 0 to 3, the y-axis goes from 0 to 30, just like it's indicated for letter A. The red is the linear line. It starts at 5, and it goes up at a constant rate. The blue is the exponential, starts at 5, and it goes up at an exponential rate. You'll want to pause here to get that copied down before moving on to the next one. So again, I have the same two equations, y equals 20x plus 5, and y equals 5 times 2 to the x power. This time it's changed the window. The x goes from 0 to 6, the y goes from 0 to 150. So we're going to start with the linear equation, and it goes up at a constant rate starting at 5. The exponential goes up exponentially, but still starts at 5. I'm now going to move this graph so you can see them side by side. Although the line appears to rise more quickly than the exponential at first, the exponential eventually catches up and surpasses the linear. So I was talking about when you first look at A, that linear line looks like it's going up faster. But then once you open up the screen, you'll see that the linear, it can't keep up with the exponential function. So why will an increasing exponential function always catch up with an increasing linear function? The reason why is because both are increasing. So both are increasing, but the exponential will always double, triple, etc., while the linear is constant. Constant.